Hello and welcome to our webinar about structural calculation with Production Assist. I'm Moritz Staffel, the CEO of DeerSoft. We are a company that is specialized in software development for the entertainment industry. Our customers include Vectorworks itself, ML Lightning, and Ruby. One of the products that you may know is Vectorworks Bracetracks. In the last 3 years, we have developed our new product, Production Assist. Production Assist is a cloud-based documentation and paperwork tool. We delivered a tool where all the information that you need to assemble an event can be stored in one place in the cloud. As you can imagine, structural calculation are a big part of this. And the structural calculation react to every changes. So when a fixture is moved, also the structural calculation needs to be updated. So, well, we got you there. Our new tools work in real time, so every change that you make has a direct impact and you see the consequences right away. This works in Vectorworks, in our Production Assist desktop app, in the browser, on your tablet, and even on your phone. Yes, you got me right there. You can do the calculation of your rigs on your phone. This webinar is one of 3 in a row. In the first, you learn the basics from a theoretical view. In the second, you learn how to build and draw the system so it can be calculated. In the third, we look into the use cases. First thing, why do we need to do a structural calculation? What is maybe not so obvious that it's mostly for documentation purposes. So when things would break, it's nice when you have some kind of document that shows that it should have worked and that the issue is not on your side. This is not forced to be a structural calculation. For example, this could also be a test construction to check. In the entertainment industry, that is often an overkill and not feasible. To be honest, I think this is true for almost 90% of the cases. The structural calculation with software is much more affordable and faster. Even for users that don't have the full structural background, Production Assist offers the possibility to check, for example, how many loads you need. Production Assist offers the possibilities to check, for example, how many load points you need for construction. That is valuable information to create an offer for trade shows, for booths, for example. The real-time engine helps you to distribute the load points so that you use their capacity optimal. Also, our new ground support calculation helps you to know the ballast that you need much better and faster, and it allows you to have a look if the construction you are planning actually is feasible. But now let's look into the requirements for doing such calculations with the program. There's a VDE 6201 that explains users and manufacturers their requirements for using such tools. So first look into what we as manufacturer need to do. We need to offer test documentation and calculation sample. We also need to ensure quality testing and documentation of the changes that we are doing internally. We do this by tracking every change that is made on our software and running so-called unit tests. Unit tests are run after every change that we make on our code and checks the calculation results against known calculation result. Currently, we have about 6,000 of these tests. In addition to this, we need to deliver a bug tracking system and offer training and support for the customers. This is something we take serious. We offer telephone support with actual engineers that know what they're talking about. One important note that is the actual liability remains at the user side, as he's the only person that can check if the software is good for his use case. Now let's look into the requirements for the users. Users working with this tool need to be qualified and have practical experience. They should attend training and education to stay in touch with the changes and improvements on calculation sites. Now let's look on what we're doing in here. We are actually booth fulfilling requirements here according to VDE 6201. We are doing training and education. VDE 6201 also has requirements on the documentation that comes out of such tool. For example, you need a table of content and consecutive page numbers. You also need to explain the structures for that an image is useful. In the chart right now in front of you, you see some screenshots from our documentation system. So on the right, the table of content for one calculation. On the left, the front page for one of the calculation, including an image of the structure. In addition to this, a project description should be added. After this, we list you all the loads that into your calculation and all the relevant changes so that you see what actually is the scope of this calculation. Production Assist works with a checkmark system. So when you look on the hoist result, you see that everything is okay and we print the green check things. When things are narrow, we print the yellow sign. When things are overloaded, we print the red stop sign. So for everybody, it's pretty easy to understand what's going on and when to stop. The FEM appendix also is needed in there. It lists all the structural information that you need to verify our calculation with another tool. That requirement also comes from VDE. But we also have a nicer tool available for this. With the QR code that we allow you to add to the structural calculation, you can link the online structural calculation. So other people also can see what's going on. They also can export a DSTV or IFC file to import in a tool like AirStab. When you work with a civil engineer on the project, that makes lives much simpler. But now let's dive into what we actually see in structural calculation. Force is one of the most basic things in structural calculation. Force equals mass multiplied with acceleration. Most in the cases we are working in here, the acceleration we care about is the gravity. The unit of force is Newton. A force is a vector, which means it has a magnitude and a direction. In structural calculation, you align the coordinate system that is used to express forces with the member. The normal force is aligned to the direction of the member and the shear force with the symmetry axis. I quickly demonstrate you this into Production Assist with a tilted truss. So in here, you see a truss, which is a little bit tilted so that it is not in alignment with the z-axis, and you're seeing the shear and normal forces. When you activate the calculation results, enable the influence lines, you can actually show you the forces Nx for y and for z. The force Nx goes into the normal direction of the actual truss. So this is the force that goes into that direction according to the truss, and this is coming out of the dead load of the truss. The shear force for y is perpendicular to this and goes into that direction, while the shear force for z goes into the direction 90 degrees from it. So that you see that the actual load of the fixture is split into two different components, actually three different components: the normal force, the shear forces for y, and the shear force for z. There are two types of forces that we need to differentiate. External forces are forces that come on loads from loads like fixtures. Reaction forces are forces that are the result of external forces. They only appear when there are external forces. So if there is no external forces, there's also no reaction forces. Reaction forces are the thing we actually care about when checking the truss, as they're responsible for the stress on the truss. Moments are also a big thing in structural calculation. They are a pair of forces with the same direction, but opposite signs. The unit of moments is Newton meter. Also, moments are vectors, which mean that they are also split into components. Let's again look into the app to understand this. I still activate the calculation result, and now show me the bending moment MBY and MBZ. This truss, again, it is tilted, so its z-axis is not aligned to the actual z-axis of the world. So if you are now in here, you see that there's a specific part going into MBY in that direction, and 90 degrees from this, there's the MBZ calculation in here as well. And you see how this is defined here in the software. There are also two types of moments. External moments, so moments that come from outrigged pipes, for example. Reaction moments are the ones that come from external forces and moments. Moments are normally the most important thing in structural calculation when it comes to the trusses, as they become hyperfast. Moments and forces are sometimes hard to read from the drawing when you don't have the background. Luckily, the deflection is really easy to understand. All bodies deform when you apply a load. Normally, human beings are really used to see objects deflect, and so can interpret this pretty easy to see if a structural calculation is valid or not. The deflection is also displayed in components, but you also can show the combined deflection that shows the addition. Let me quickly demonstrate you this in the app. So to activate the deflection of a system, you need to activate the dy, dx, and dz. You see that are the components that are moving the truss for dz into the direction of the truss, for dy to the left of the truss, and dz to the bottom of the truss. You also can display the so-called combined deflection figure, which shows that the actual structure is going straightly down, so it's a little bit bending about both axes in here. That is enough basic knowledge for this. Now we come to the Eurocodes. The Eurocodes are the standards that are used for all the calculations that we are doing with Production Assist. As the name indicates, the Eurocodes are a European construct and apply for all events inside Europe. The Eurocodes are divided into 10 parts. The first 2 parts define the load part of the calculation. The other 8 parts define the resistant part of the calculation. There's one Eurocode for each steel, aluminum, and timber structures. The main idea behind the Eurocode is that you calculate the impact and resistance separately and then check if the resistance is higher than the impact. The nice thing as well is that you can mix multiple materials. If you prove wood, steel, or aluminum, the impact is always calculated via the Eurocode 1 and 2. You just swap in the other Eurocodes for timber, steel, or aluminum. The first thing that you need to know is that the Eurocodes assume that all loads are addressed. The Eurocode says when that is not the case, you need to check the consequences yourself. We look later into the dynamics. Besides this, the Eurocode notes 2 types of loads, permanent loads and variable loads. Permanent loads are things like dead load and are applied to the structures all the time. The safety factor is 1.35 when it's unfavorable, so a damaging load, otherwise 1. So why does things get a load factor? Normally, when you assume the weight of things, the things could be heavier than you thought, or maybe a little bit differently built. In order to compensate such effect, you choose a safety factor so that you stay on the safe side. So even when things are a little bit different, it will still be safe. Variable loads are all things that are not permanently installed. The Eurocode mentions here payload, wind load, and snow load, for example. Have in mind that the Eurocodes are crafted for buildings and our entertainment structures are not really intended when writing these codes. In a building, the payload is normally not really clear, but for our structure it is. Unfortunately, we still need to take the high safety factor by 1.5 for our loads. This is really, really important, as otherwise you make a problem, an error to the unsafe side. The safety factor for favorable impacts is 0 for this. That makes sense when you think about snow load. If your structure is only holding up when there is snow, we have a bad time in the summer. For hanging structures, there are normally no favorable loads. But when you do ground support calculation, there are. So for ground support, you need to take this into account. How this is handled by Production Assist? All objects that you have get assigned a load group like dead load or payload. But this indicates, you can indicate which safety factor will be used inside the calculation. The assigning of the load group normally goes automated. So everything which is a dead load, for example, trusses and hoists go into dead load, while all other objects normally go into payload. You can customize this for specific cases. For example, if you want to do ballast calculation or some special load cases where you want to play with these things. So the Eurocode, when you're running a calculation, lets you check 2 things, the ultimate failure and the usability. ultimate failure checks actually if things will break. This is a hard criteria, so you check if the truss can actually handle the load. The usability is a little bit more soft. You check if the system is suited for the intended use. Normally you check the deformation and vibrations. People are used that the structure do not deflect that much. So when you're hanging a structure on a trade show, they expect that the trusses are straight and don't have a huge deflection. Deflection actually does not hurt the system, so it's more an optical thing. So people that are standing behind under a structure, which is really bending a lot, they're feeling uncomfortable. And for sure, you don't want people to feel uncomfortable. In production assist, we have load combinations for this. Each load combination stores the safety factors for a calculation. You're seeing this at the top right in here. So you're seeing the load factors that are used for calculation for Eurocode ultimate failure. The nice thing is that production assist does the calculation for boost usability and ultimate failure at the same time. The green load combination is used to calculate the trusses and their workload, while the actual deflection calculation is done with the blue load combination. This is also used to prove the hoist. So you don't need to calculate 2 times like with other software. It just works with one calculation in here. The actual proof from the cross-section is then done basically with this formula. It calculates the resistance from impact and compares it with the impact itself. When the impact is smaller than the resistance, then the proof is good. Depending on the type of resistance, there are different safety factors for the resistance side. So for example, a normal safety factor here is 1.1 for stress capacity on cross-section according to Eurocode 9. For example, the stressability in case of fracture failure to tensile loading is 2.5. So depending on the use case, you need different safety factors in there. The good news is that for trusses that already have been done by the manufacturer, they just give you the resistance values that you need to use. In PA, you find the information about the workload in the structural tabs inside the worksheets. This shows you the information in real time. So every time you're changing something in the drawing, it automatically updates these tables and you see how much your structure is used. Also in the structural report, you see this kind of information. On the first, thanks to the left, it lists you the relevant forces and moments in a table. So for each of the different cut reactions we just saw, it gives you the maximum value and all the other values at the same point. It then lists you the geometry of the truss and the design values that you have. After this, it done all the proofs again that we need for this. One thing that is worth pointing out is that it automatically also calculates interaction of bending moments and shear forces at the connection forces. That is something completely new in our products that none of our other products actually can do. Okay, that was a lot of information. Now let's jump into something more practical, but really important when you're doing the actual structural calculation. So we start with 2 hoists on a system. So something like this, really easy. You have a truss loaded by dead load, and you have 2 hoists to the right and to the left. The calculation for this is really, really easy. So you have the sum of forces and sum of moments around a point. Then you easily come up with the solution that half of the load is going into the left point and half of the load is going into the right point. Let's have a look onto this into the production assist application. Note that the calculation that you are doing in here can be also done, for example, with Vectorworks, with the browser, or any other tool where we run under, for example, the iPad or the iPhone. Here we have added up our system. So we have a hoist on the left and a hoist in the middle, and it's only loaded by the truss and its dead load. So half of the load goes into the right one and half of the load goes into the left one as expected. The nice thing about the 2 hoist systems is when you move the hoist up and down, so if you're changing the trim heights, it still have the same loading like before. So if I'm giving here a chain shorten value by 50 millimeter, so if I move this here up by 5 centimeters, the load does not change in here. Same in the other direction. So if I'm going down, it is still not changing the load in here. That is really useful because this doesn't enforce you to level your rigs when you are building structures with just 2 hoists, and is really valuable. Now let's move on. Unfortunately, you don't always have the system. Actually, it's more common to have more than 2 hoists on the system. So let's look onto what's going in here. So we're talking about a system like this. So 3 hoists, only dead load for the truss, and a middle hoist and 2 outside hoists. So when you're doing the calculation that you have learned in school, you end up with this kind of calculation. So, well, not really the one that you can solve because you have 2 equations, but 3 unknown values. And that is something that you can't solve without choosing a parameter. So let's have a look onto production assist as well, as for sure we also help you with this. So we have the same system in here, or a similar system like before. So about the load to the left is almost half what's going into the middle, a little bit more, and to the right. So what normally people tell me when I ask them how the load is distributed, they say about 60% of the load go into the middle and 20% of the load go into the right and left, which obviously seems to be true. But what is now happening if you move up this hoist in here? For this, we apply a chain shorten value. So let's start with 15 millimeter. If I'm entering this, you see that the load on the right and the left have increased and the middle has gone down into this. Now let's move on and type in 400, which is 40 centimeter, and you see what is happening now. So right now, the load is almost fully distributed between the left and the right hoist, and the middle almost got nothing. If I'm now playing more with this and giving it a 500, you see that it's even going out of force, the middle one, and don't get any force anymore. If I'm typing 200 in here, you see that it's now the left and the right one are getting more forces. So the say that 60% of the load go into the middle and 20% go into the outer one is only true if it's perfectly leveled in here, which obviously can be hard to achieve in here. Let's look a little bit more into the math of this so that you get an idea about it. So the equation that we need in here is a little bit fancy. So we're doing differential equation right now in here. So the thing is that the deflection function is the force integral of the negative force function in here. If you're doing the math behind of this, and we are a little bit lazy, so I've just written in you end up with just 2 functions in here, which are valid in the first part and the second part of the actual calculation. So we don't do into too much math, but we look into the results in here. So what we do in order to solve this is that we pick specific points where we know the value. The first value that we know is that the deflection at the starting point, so where x equals 0, also is 0. So if we insert 0 for x, we end up for the term x square 4 for 0, for the next term x whole 3, 0, for the x whole 2, 0, c cos x 0, and then it stands in there c equals 0. So that is how you solve this. You can go on. I've printed you all the information, all the values that we know about this system, and it gives you an idea on how to calculate this. The most important part that you need to take out of this is that the actual deflection, the actual loading figure of the systems is only depending by the trimming of the trusses. So if you don't level your trusses accordingly, you run into a problem and you don't get the results that you want to use for this. We also have an example for this that shows you some special thing in here for the actual drop compensation in here. So what we often have is that we hang one truss below another truss. You see that this truss is hanging near this hoist in here. So the deflection of the hoist is really small at this point and going down. The second thing in here is going in here. So you see that it has also a different deflection in here, and it gives you this information. We have a cool feature in here that is called calculate compensated chain shorten values. That will automatically calculate you the new values when you level this correctly in here. The new functionality we have added to this is that it allows you to select that you only do this for specific hoists. In order to check this, show this you a little bit, I pick this line of truss and move it a little bit to the right so that it's both at points where the deflection of this is a little bit more. I select this hoist and tell him I don't want it to be compensated, removing the existing chain shorten value and rerunning the menu command calculate compensated chain shorten value. This will now level this hoist as it can be leveled, but will not level this here because it's a rope in this calculation. So it's a way to combine, have the to check the influences of ropes and into addition with the hoist in here. So if you're moving this around, it's always changing in here depending on the deflection. For this, we have a system which is automatically doing this when recalculating. It has the auto adjust chain shortens. When I'm doing this, it will automatically, whenever I move it, calculate me the compensate chain shorten values for the hoists that are marked as compensated. Okay, that's pretty tough with this and the cool functionality, and you see that the values are updating in real time. Last thing that we have prepared for you for this webinar is that we have a look on the impact of corners inside the calculation in ground supports. For this, I've prepared a small system which looks like this, right? Which looks like this. So it is a standing ground support in here. I've moved the calculation results a little bit up so that you can see them more easier. And it has corners in here, so normal L corners with this. You see that the maximum moment that is in the middle of the truss is 18.3 kilonewton meters. When you're activating the workload for this, you see that everything seems to be in a safe space, so everything is green in here. This calculation is done without the effect of the actual corner. So it is assumed that this corner is to some level rigid. In Production Assist, you have the option to enable that it actually calculates the corner with it. And the results are stunning. So if I'm changing this now and I'm using the right corner geometry in here, you see this in here so that it's actually using each of the internal webbing. You see that also the moment changes. It changed from 18 to almost 22. That is a 830V. The 830V can almost take 24 kilonewton meters. So by this, you're almost into a site where you're at the capacity with this specific thing. If you now look into the workload in here, you actually see that the truss is overloaded. So it's about 600% workload. So in this case, if you do this specific setup, then you will break this. We have in the middle a generic weight, which is about 500 kilos for this span in here. If I'm deleting this, so only the system with that load and nothing else is still at 85% workload. So the assuming of the corners and the right calculation of this is pretty important for our calculations in here to have in mind. Okay, thank you very much for this. That was the first part of our webinar. The next webinar we are doing is about paperwork and how to generate it with our tools. The next webinar for the structural calculation, I think, is in 2 weeks. And then we jump into the drawing of the system and how this is actually working so that you know how to assemble your rig.